But now we're going to start looking at motion that's a little bit more complex. So maybe they move forward, maybe then they move backwards, and then they speed up, then they slow down, then they do whatever. But when we talk about complex motion, it's going to be easiest for us to represent it in a graph. Okay? So a position versus time graph is what we consider to be a motion diagram, right? Motion diagram is any sort of visual representation of motion. And so a position versus time graph is just an example of that. Okay? This is what a position versus time graph looks like. There we go. Okay, this is a really, really simple position versus time graph. Time will always be on the x-axis because that's the thing that we control. We're looking at how often our time changes. And then the position is literally wherever they are at that time. Okay, wherever they are at that time. So when we talk about position versus time, position always goes on the y-axis. And that's measured in meters. And then time goes on the x-axis, and it's almost always measured in seconds. It's very, very rare for it not to be measured in seconds. Okay, that's what's called position versus time, right? Dependent variable versus independent variable. So in this motion, in this graph, what's happening with this motion? What are they doing? Are they moving forward? Are they moving backward? What are they doing? They're moving forward. And are they moving forward at a constant rate? Yeah, right, because we have a straight line. We have a straight line slope. What would it mean if our slope looked like this instead? What if our slope looked like this? What would that mean? Yeah, we're just moving forward faster. We're still moving at a constant rate because the line is straight, but we're moving faster. And if our line looked like this, we'd still be moving at a constant velocity, but our velocity would be slower, right? Does that make sense how those two things work? What if our graph, instead of the red line, let's get rid of that, instead of the red line, what if our graph looked like this? What would that mean? Yeah, we're moving backwards, right? We start at 6 meters in front of a starting point, and we move backwards. Good. So those are some examples of position versus time graph. This is really, really important. The slope of the line on a position versus time graph tells us velocity. The slope of the line tells us velocity. We can calculate velocity based on the slope of the graph. That's super, super important. Slope of the line is velocity. Okay. So in this example, if I was going to calculate velocity, do you know how to calculate the slope of a line? The equation for slope is the change in y over the change in x. Agreed? That's how we calculate slope of any straight line. Is that ringing a bell from math? Okay. So if I look at this actual graph, this is displacement, x. This is time, which is t. So if I was looking at this, if I was going to calculate the slope, it'd be like change in x over change in t, and that's equal to velocity, right? The equation for velocity is my change in displacement over change in time. So that's the reason why I see this slope of the line giving me my velocity value. Okay? So I can pick any 2 points. Let's say I pick this one and this one. So if I look at my change in my displacement, that means I'm going to go 4 minus 0 over 2 minus 0, and I get a velocity of, a velocity of 2 meters per second. Agree? You know how we calculated that? This is change in t, change in displacement. Okay? 2 meters per second. So that means after 2 seconds, I moved 4 meters. After 1 second, I moved 2 meters. Right? So it's following exactly like it should. Questions about how we calculate that? Okay. All right. Let's look at now this a little bit different version of the graph. We know that the slope of the graph tells us velocity. So what does it mean to have a negative slope like this in this example? What's that mean to have a negative slope? Yeah, we're going backwards. So when we talk about a position versus time graph, this 0 mark is our starting point. And so let's just talk through what happens in this graph. From 0 to 2 seconds, what are they doing? From here to here, what's happening? Are they moving or not? No, they're standing still, right? Our graph is not changing from 0 to 2 seconds, which means they're standing still. Okay, from 2 seconds to 5 seconds right here, what are they doing? They're going backwards. And are they going backwards at a constant velocity? Yes, because they have a straight line slope. From 5 to 7 seconds, what do? They go forward. And what happens when we cross the x-axis? What's that telling us? We're going past our starting point. That's it, right? We go past our starting point. And here, are we moving faster from 5 to 7 than we were from 2 to 5? Are we moving faster from here to here than from here to here? I would say yeah, right? Our slope looks steeper. And if we have a steeper slope, that means we're probably moving faster. We're covering more distance in a shorter amount of time. So I'd say we're moving faster there. All right, from 7 to 12, what are we doing? Are we doing what? Yeah, we're standing still. Our position is unchanging. From here to here, what are we doing? We're going backwards slowly or quickly? Quickly. Then we go here and here. What are we doing right there? We're going forward, but have we reached our starting point again? Nope. Then we stand still for a minute. Then we go forward. Then we stand still. Okay, can we talk through what's happening in those scenarios? You're going to have to be able to write that stuff out. Right? Okay? Like you would have to say from 0 to 5 seconds, 0 to 2 seconds we stand still. 2 to 5 we go backwards, blah, blah, blah. Those are the types of things you have to be able to spell out. I don't need you to look at that. All right. So let's do a couple examples here. I want you to tell me what's my velocity from 1 to 3 seconds. What's my velocity? Oops. What's my velocity from 1 to 3 seconds? Okay, so how would I go about finding my velocity? What do I have to calculate there? To calculate velocity, what do I have to find? Other way around. Displacement over time. Good. But more specifically on the graph, I have to find the slope. Right? To find velocity, I calculate the slope. So that means, right, 1 to 3 seconds is right here. Right? 1 second to 3 seconds. Here to here. So if I want to calculate that slope, right, this point is 360. This point is 120. So to calculate my slope, I'm going to go 60 minus 20 over 3 minus 1. Is that right? Is that what you had? Change in y over change in x, or change in position over change in time? Give me like a head nod if that's what you had. Yes, okay, I can't read you guys with masks. Everyone looks the same. Okay, any questions about how we calculated that? Okay, if you don't ask questions, I don't know if you don't know. Now tell me, what is my position, or what is my displacement at 4 seconds? What's my displacement at 4 seconds? Okay. How do you think we might find that? What's my displacement at 4 seconds? Here's 4 seconds. And what do you think displacement, what am I looking for? Tell me what displacement means. Good, good, okay. So if I'm asking for displacement at 4 seconds, I'm trying to find out where am I in comparison to my starting point at 4 seconds. So how would I read that? I just go over and read the axes. Okay, so if I say, what's my displacement at 4 seconds, my answer is just 60 meters, right? I'm 60 meters away from where I started, right? Here's my starting point. At 4 seconds, I'm 60 meters away from that. So that's my displacement. All I do is read the graph. Okay, read the y-axis of the graph there. Okay. Even though my official starting point was there, that's not what I care about. I care about it in comparison to the graph starting point. Does that make sense? Okay. So that one's super easy to find displacement on. Okay, tell me this time, I want to know what, I can't spell what is my velocity during time frame A on the graph. Okay, what's my velocity during A? What'd you say? 0.75 meters per second. Yeah. We agree? Right? We're going to do basically 30 minus 0 over 40 minus 0. So 0.75. Good. Okay, good. Now go ahead and find my velocity during C. C starts right here. Okay, and go ahead and stop it right there. Okay, find my velocity during C. Is that what you had? Good. What's the negative tell us here? We're just going backwards, right? That's what the negative tells us, is we're going backwards. Good. What's my velocity during B? What's my velocity during B? Is my position changing during B? And so if my position is not changing, that means I don't have any velocity, right? I'm standing still during part B, so my velocity is equal to 0 meters per second, right? I'm not moving during that. My position is unchanging during that 40 seconds, right? So even if I did the math, I'd go 30 minus 30 over 40, right? So 0 over 40 is 0 meters per second. Right? So anytime my position is not changing, my velocity would be 0. Okay, questions about that? Okay. Let's do a little review here, and then I'm going to send you into a review with CK12. Oops. I want you to try one velocity review problem, and then I'm going to have you do a CK12 real quick, okay? So how far can a cyclist travel in a 2.5-hour trip along a straight road if her average speed is 18 kilometers per hour? Okay. I'm okay with your answer here being in kilometers. Okay, you can keep your answer in kilometers in this one. Remember here our equation for velocity or speed, right? Same essential thing. It's going to be displacement over time. Change in displacement over time. So I was given my velocity. My displacement is what I'm solving for. Change in displacement. Does everyone know? I didn't really go over what's that sign mean right there? What's the triangle mean? The triangle is called delta, and that means change in. Okay, really what the delta means is final minus initial. So delta x, or change displacement, means x final minus x initial. Right, that's really all that means. And we're going to use that delta a lot. I should have been more explicit about that earlier, but change in position over time. So if I want to find displacement, how do I solve for that? Do I multiply or do I divide? If I want to solve for this, what do I do? Multiply or divide? I multiply, right? And I get a change in displacement of 45 kilometers. Right? We don't have to include a cardinal direction there. It technically only asks for speed, and we weren't given a cardinal direction to start, so we don't have to give one there. Now, basically a different type of graph. We looked at position versus time first, and that's where our graph shows a change in position. And then we're going to look next at something called a velocity versus time graph. So now instead of position being on the y-axis, it's velocity that's on the y-axis. So if you look at this graph right here, position versus time, this is moving at a constant velocity forward. Would we agree? Moving forward at a constant velocity. This graph shows the exact same motion forward at a constant velocity. Okay, but it's a velocity versus time graph, so they look different. Because instead of position being on the y-axis, velocity is on the y-axis. Okay, so they both depict the same motion, but the graph looks very different. Okay, so in this case, velocity versus time graphs, you have to really pay attention to this axis means 0 meters per second. So now if we would approach the x-axis on a velocity versus time graph, that would mean we'd come to a stop, right? And then below the x-axis would mean we're moving backwards. So it's a little bit of a different feel. Okay, so let's get into velocity versus time graphs a little bit more here. All right, in this case, on velocity versus time graphs, we see that the slope tells us what we call as acceleration. The slope tells us what is our acceleration. That's new for us. We haven't got into acceleration much. Okay, we haven't got into acceleration much. But acceleration is any sort of change in velocity. Okay, it tells us what change in velocity we have. Okay, how do we define the displacement now from a velocity versus time graph? How do we find how far we've gone from velocity versus time graph? This is how you do it. We find the area under the graph. Okay, we calculate the area under the graph. And let me expand this a little bit more. To the x-axis. Okay? We find the area under the graph to the x-axis. And that seems really arbitrary for you right now. That's okay. Okay? But when I say find the area under the graph, we're going to do this. From 4 to 5 seconds, for example, here's 4 seconds, here's 5 seconds. I'm going to complete that shape, whatever shape it is, right? 5 seconds is here, 4 seconds is here. I'm going to complete the shape. And in this case, it's a triangle, right? So do you know how to find the area of a triangle? Yeah. Right? Length times width divided by 2. So all I want to do is really find the area of that triangle. So this side of my triangle is 1 second. This side of my triangle is -2. Right, -2 meters per second. So when I do that, I'll go 1 times -2 divided by 2 equals -1. Right? And so my units for this are meters per second divided by seconds, because I'm going to take my velocity on the y-axis, which is labeled meters per second, and my time is labeled in seconds. So when I take change in y over change in x, that gives me meters per second, or meters per second squared. That's how we're really going to see that written. Meters per second squared. Okay, we're going to get into what acceleration really means, but I want to introduce it on the graph first. Okay, so let's think about it more specifically, or a little bit bigger picture. Let's talk through exactly what's happening on this graph, right? We know how to do the things. Practically, we know how to calculate them, but I want to figure out what do they mean, okay? So from 0 to 2 seconds, what are we doing? Knowing that this is velocity, not displacement, what are we doing? We're going from 0 meters per second to 1 meters per second to 2 meters per second. We are speeding up. Agreed? We're speeding up in the positive direction. Anything above the x-axis here is, let me see if I can get this graph a little bit bigger. Okay, no. Anything above the x-axis here is positive velocity. Nope, this is not what I wanted. Anything above the x-axis here is positive velocity. Anything below the x-axis is negative velocity. Meaning here we're moving in the positive direction, here we're moving in the negative direction. And we said the x-axis itself is 0 meters per second. This means we're at rest. Okay, so in our other graph, if we had a straight line here, that means we stopped moving. But in our velocity versus time graphs, it means we're speeding up, and then what happens here? We're same speed. We're not stopping. We're still moving at 2 meters per second. So we put the cruise control on, right? We stop accelerating. We stop speeding up or slowing down. No. What's going from here to here? We're slowing down, but are we still moving in the positive direction? Yes, right? Because we're still above the x-axis. We still have positive velocity, but we're going from 2 meters per second to 1 meters per second to 0. Right? Then what happens after that? We speed up in the negative direction. Right? You're going to see me run into something pretty soon. Here we're speeding up in the negative direction. We're going from 0 meters per second to -1 to -2. Remember, the negative doesn't tell us numerical value. It tells us direction. Right? So we go from 1 meters per second to 2 meters per second west, or whatever. Then what happens here? Are we speeding up or slowing down right here? This one's tricky. We are going toward 0 meters per second, right? We're slowing down in the negative direction. That's tricky, really tricky, right? It doesn't really make sense that we would have a positive slope, but we're slowing down. But we need to think about it as we're approaching 0 meters per second, which means we're slowing down in the negative direction. Yes, kind of? Okay, I know this is a little bit much, especially after that first one. Let's walk through what's happening in this graph. Let's just talk through this one. Okay, from A to B, what's happening? We're speeding up. And do you see how this is all above the x-axis, which means we have to be moving forward this whole time. Okay? We're speeding up, then what? Same speed. B to C is same speed or cruise control. From C to D, what are we doing? Speeding up. D to E, same speed. E to F, we're slowing down. F to G, same speed. And then G to H. speeding up. So we went the same direction. We were going forward that whole time. But we just went slower, faster, whatever. Okay, good. Okay. Oh, I don't want to talk about that. Okay. We already found that. Let's look at this one. We want to find the displacement. We want to find out how far did we travel. That's what displacement means. From 5 to 8 seconds. From 5 to 8 seconds. So here's 5. Here's 8. I'm going to draw the lines out a little bit more clearly here. 5 to 8 seconds. That should connect, but it doesn't. 5 to 8 seconds. I want to find out how far did I travel during that time. I was traveling at a constant rate of 40 meters per second for 3 seconds. Okay, but here's how you do it. You find the area of that section of the graph, right? We want to find what's the area of this portion of our graph. We know it was 3 seconds, and our side, this side is 40. So we go 40 times 3 is 120 meters during that time. That's how far we traveled. Does that part make sense? If you think about an even bigger picture, I was going 40 meters per second for 3 seconds, right? So 40 meters for the first second, 40 meters for the second, 40 meters for the third. That gives me 120, right? That's pretty easy to calculate that way. And it's easy to see even without doing the area calculation. Does that make sense? Good. What if I asked you for what's our displacement from A to C? That's a little bit trickier, right? We sped up from 0 to 20 during 2 seconds. That's kind of hard to think about how many meters we traveled during that time. That's not as easy to see. And then you've got constant speed for a little bit. So what we do is we break this into shapes we do know. So now I've got 2 shapes. I find the area of each and add them together. Okay, so let's go ahead and do that. This triangle, I have a side that's 2 seconds long, and this side right here is 20. So I would go 20 times 2 over 2, which is 20 meters during that first 2 seconds. Right? 20 meters during that time. And then over on the second part of it, I traveled 2 seconds and still 20. So I go 20 times 2 because it's a rectangle, so I don't divide it by 2, and that's 40. So I add those two together, and I get, during this time right here, I traveled a total of 60 meters. Okay, does that make sense? If I were going to ask you for displacement that was below the x-axis, that would be negative, so you'd subtract that. Right? But this one is all positive, all moving forward. Okay, so that means from 0 to 4 seconds, I traveled a total of 60 meters. Okay, these 3 go ahead and do on your own. We're going to have 3 different answers here. This is why. See how the x-axis is labeled by 2's? Okay, 2, 4, 6. So if I find the slope from here to here, I would go 2 over 2, which I think is only 1. Right? 0 to 2 seconds is here to here. So I would go 2 minus 0 over 2 minus 0, and I get 1 meter per second squared. Yeah? That makes sense? This one's tricky because you don't see it. This side's labeled by 1s and this side's labeled by 2s. That makes it a little bit tougher. Okay? Find the displacement the object traveled from 8 to 10 seconds. Sid, what'd you have on this one? 8 to 10. So this would be 2 times 2. So 4 over 2 would be 2. And if it's displacement, it's just meters. Right, just 2 meters. Yes, but that's what I had, 2 meters. Okay, so this is displacement. You're just looking at how far they went. Good. And then, Kanta, what's the object's velocity from 16 to 18 seconds? -2. Good. You're just reading the velocity here. It's not stopped. It's not at rest. It's moving -2 meters per second, constant. Very good. All right, good. Are you feeling pretty good about those? Kind of. I know this one is a little tricky. This one makes us think a little bit more, and then it's really easy to get confused between one and the other. Okay, last thing I want to show you about. I want to see. This is going to be included in our activity. Okay, and we're going to switch gears back to position versus time graphs. Okay, we're going to switch gears back to here. Okay, and there's a way that we can show speeding up and slowing down on position versus time graphs. Okay, and you have to see the relationship between the two. So I'm going to draw out 4 graphs. Four graphs, okay? And these represent a lot of different types of motion. Okay, 4 different types of motion to be exact. Remember, let's think about this is meters and seconds, or position versus time, position versus time, position, time, and position, time, right? But these show a change in velocity. So it's not just speeding, it's not just going straight in the forward direction or going straight in the backward direction. This is speeding up or slowing down. So I want us to start thinking about what do these graphs represent. Okay? So let's start with the first one. Position versus time. First thing I want you to look at is it moving in the forward direction? Yes or no? Yes. So we're moving in the positive direction. Positive direction. And do you think we're speeding up or slowing down? Speeding up. You're right. But what makes you think that? Well, the upward doesn't have anything to do with it. The upward has to do with the positive direction. We go from a really shallow slope to a really steep slope. Right? So this means that we are speeding up. Okay? I don't want you to just memorize these. I want you to actually be able to think about, like, okay, right here it looks like we're moving pretty slowly, right? Because our position is not changing much. Here our position is changing a lot, so we're speeding up then. Okay, this one right here. Are we moving in the positive direction or the negative direction? Oh, we're looking at this one right here. Are we moving in the positive direction or the negative direction? We're moving in the negative direction. And are we speeding up or slowing down? What do we think? Are we speeding up or slowing down? I think you're speeding up. Because look here, we're not traveling very fast right here. And then all of a sudden we've got a really steep slope. So this is negative direction. Speeding up. Okay? This one down here. Right, we need to make sure we understand all of them are moving in the forward direction. Okay, this one down here, what do we think? Moving in the positive direction or negative direction? This one. Negative direction, good. And are we speeding up or are we slowing down? Slowing down, right? We know because we already have one that looks like that. But we're slowing down because we go from a really steep, really fast slope to now not moving very fast at all, right? A really shallow slope. Last one, what's the combination have to be? We're moving in the positive direction. And what are we doing? Slowing down. Good. So now we're in this activity we're going to do, you're going to have to match the position versus time graph to the velocity versus time graph. Okay, you're going to have to look at a position versus time graph and say what's happening, and then how does that translate to a velocity versus time graph. Okay, those are the things that you're looking at. Okay? So